very much for your kind introduction. So welcome, good afternoon, everyone. Thank you very much for being here today. Today, I want to speak to you about design in VR and how we want to revolutionize the whole simulation world. We want to change everything, so each one of you, without having any knowledge, can make his own design and perform simulation really fast. And how we want to do that, I will show you here. So, but first, let me start. I'm coming from the company Siemens AG. Perhaps you have heard this company. Currently, we are doing one of the major changes in our history. We are carving out our gas and power division. So now it will be called Siemens Energy, and we are focusing on smart infrastructure and digital industry, so we will become a software and digitalization automation company. We have multiple departments, and I'm coming from the department Corporate Technology, which is the central R&D department of the Siemens AG. So what we are doing in the Corporate Technology, just a brief view, we are doing research in the digitalization and automation, as I said before, and we have eight major technology fields, from AI and data analytics to autonomous robotics, and then till to simulation digital twin, where I'm coming from. Our main goal is to let's say, generate the algorithms for the next generation, make that faster, the simulations, and one aspect is the human digital twin interaction, and that's why I'm here today. Oh. So, what my group is doing in the human digital twin interaction is we want to disrupt all the human interactions with the computers and their systems along the product life cycle, from the concept till the services. And how we do that. Here I have some examples to show you, some of our prototypes, some of our demonstrators we have developed the last 2 years in our department. I hope it starts with the right one. No. So here the first one, it's called FM in VR, where you can perform finite element analysis in the virtual world really fast without having any knowledge and get interactively feedback for your actions. It's part of our bigger design concept in VR. I will go into details later how it works. As you can see here, everything performs real time. Then we have another example here for the design phase, with the virtual planning of blowers in buildings. That's here an application that's thought for architects. So when they design a building, they can perform some CFD simulation. CFD is computational fluid dynamic simulation without having any knowledge and capture some phenomena. In this case, they can place a smoke source in the building and interactively see how the smoke will propagate in the building and take the appropriate countermeasures at an early phase. Such projects could become very useful here in Germany, especially. We have some bad examples of big projects like Stuttgart 21 train station, when they found later, after constructing, that they placed at the wrong place the exit doors. Then we have some examples here also from the production and the planning. Here, for example, it's a robot milling, so now we will want to enable that the robots can perform some manufacturing processes, but the robots are not accurate because of the stiffness. And in this example here, the user can interactively place the object in the 3D room and get a feedback. What's the quality of the milling process? You can see the error on the diagram and the stiffness of the robot. So interactively, he can figure out what's the best position to place later his object for robot milling. And then we move to the operational phase. That's Dirk. Dirk and me presented last year this demo where we managed to visualize real-time the 3D geometry of a motor. We took, for this example, really detailed 3D engineering models. We applied some mathematical algorithms, and we reduced these models to perform real-time. And with the help of our neighboring department, we're visualizing everything with the HoloLens real-time. And here you can get the information like the temperature of the motor at any location inside without having any sensor. Another example that we have is this one from the Hanover Trade Fair, which is one of the highlights of the Siemens during the Hanover Trade Fair last April. That's for the process industries, where we have an application where you can see overlaid on the real object some information. When you go closer to the object with your iPad, you can see exploded what's inside of this part. You can get information for this part. And then we have there some videos, some technical details, how you can perform some maintenance. For example, in this case, how you can change the screen you can see there on this equipment. And as you move around of this object, you can take some more information. For example, here, you can see some key indicators or some P and ID diagrams. And if you look upper, you can have, for example, some sensor data. The sensor data in this application are not real-time, are installed in the app, because real-time internet at trade fairs, it's a little bit tricky always. And finally, for the services, that's our brand new training platform. It's called Varina. It's completely developed by Siemens. So it's a training platform where you can manage all your trainings, you can access all the trainings, you can edit them, so you can remove steps, you can add steps to this training, and of course, you can generate your own new training. Thanks to our VR authoring tool that we have integrated there, you don't have to program anything, but all the tasks are monitored during the VR interactions. And of course, in the video, in this VR authoring, you can add videos or annotations that they are kept there for the next people who are going to carry out the training. And what's great about this platform, it's that all the steps from the VR training or the authoring can be exported for AR guidance with the HoloLens, as you see in this example. So you don't have to program again the training for the field technicians. You do that only once. But that's all with our work. And let's go now to our topic today. So, why we are here today, we're going to discuss about that today. Market trends require new disruptive methods. So we want, and especially in the early concept phase. Why is that? Because now the time to market for the project is shorter. The customers want novel, innovative products. As you can see here, that's from Topology Optimization, an example. But we have lack in experts in the pre-development phase because the experts are engaged at the later stage. So let's go in more details. Why about the pre-development phase? Why we're targeting this phase? Because now this phase is the main bottleneck of the completed product development. 80% of the costs occurring during the early design phase of the product. And why is that? Here is an example how it works now, this iterative method. We have in my company, for example, that's quite common, that different experts are distributed around the world. For example, we have a designer in the US and the experts in Europe, China, and India. So what happens now in the early design phase, the designer makes a new design, and he sends the design to the experts to evaluate their properties. And each of this expert carries out some simulation for his field of expertise, and then he sends back to the designer his feedback. So we have pure silo development. Nobody knows what the other is doing, but all of them are strongly dependent from each other. And that's not efficient, and of course, we don't have an optimal allocation of our resources, because the designer waits till he gets feedback from the others, and the others from the designer. So it's not so effective, and we want to change that. You may ask, okay, but why the designer doesn't do another job while he waits? Because currently we have a high entry barriers for the CAEX tools from non-experts. And what is a CAEX tool? X can be a D when it's a design, and with a CAD tool, we can construct the geometry of the model, and if it's E, it's computed edit engineering, and with these tools, we can test the functionality of a product before even building it. But let's go back and see what we are an R&D member outside of our domain of expertise. And we say, okay, let's give it a try. We have to face three major problems. Tools, first of all. There are a number of tools on the market there, which is the right one for me. And if I choose this tool, can this tool work with the other? I don't know, because I'm not an expert. Then it's the usability. Most of these products have a rather complex UI, and the visualization of the products is really low and difficult. It's not trivial. So I have to use 3D mouse. How works that? And finally, the terms. When you open these tools, you get some terms like meshing, turbulence, eigenfrequency. What's that? I'm not an expert. So you see that all these barriers do not allow to people not knowing this field to enter and try. Therefore, what we say is that we need a new workflow in the early design phase, which is user-friendly, is interactive, so the user gets instantly feedback for his action, It can cover multiple simulation fields, and last but not least, has a really high resolution. So, but why now? You may ask me why you are saying now about the pre-development and why you want to improve that now. Because the last years, we have major leaps in electronics and computer science. So the computer power is growing faster than the Moore's law thanks to GPUs. We have major breakthroughs in the mathematics because now exponential capability growth of algorithms improve the applicability and usability of simulation-based models and or database models. And finally, that's the most important, virtual augmented reality enters the industry. Now all these consumer technologies like AR, VR become mainstream in industry, and they can help us lower the barrier entry for non-experts. Having in mind the three factors before, and these two key building blocks that we have developed in our in-house. The first one, it comes from us. It's a completely new GPU-based 3D physics solver that's developed by our department, and it performs interactively. It's 1,000 times faster than the state-of-the-art solvers, and it's based on voxelization. I don't want to go into details, it's pure mathematics. If you want, you can discuss later about that. And the other one came later to our department. It's the Vario VR goggles, which Siemens Corporate Venture, Next 47, invested on this company last year, and since April, we're using these glasses. And this, thanks to these glasses, it helps us further to reduce the entry barriers for the non-expert, because we started working with the other VR glasses 2 years ago, and there were some issues with the quality, the visualization, and they couldn't read so much stuff, so there were some problems, but thanks to the Vario, all these problems were resolved. And of course, the Vario offers us the eye tracking, which is a completely new way of interacting with the virtual world. Oops. So, taking all that with these two key building blocks, the design concept in VR was born. It's a project that runs more than 2 years in our department and consists of 4 different blocks. First of all, on the upper left side, you can see the design generation, where you can make a 3D sketch really fast. A really coarse idea can be tested in the 3D world instead of using a really complex CAD tool. And how it works? We call it that CAD and VR internally. You can see all the functionality, the basic functionalities are on your controller, and by swiping the pad left and right, you can access all these functionalities. From a primitive objects that predefined there, or functionalities, import, exported geometry. But how it works, let's have an example here. So we select a box with another controller. The box is created in the virtual world, and with the 2 controllers, you can adjust the dimensions really fast without having to type anything. And you place the 3D object in the room. After that, you can repeat that for the other primitives. For example, here a cylinder. Why cylinder? I want to make a hole. That's why I want to show you how you make holes really fast. And what's here new, we have integrated a virtual grid, as you can see here, because the perspective, the 3D world is really difficult, so we cannot align the objects in the 3D world perfectly. But thanks to this 3D virtual grid, as you can see, we can align the objects better. For example, here we put the cylinder in the object, and now we want to subtract it. We select both of them, and then we can perform really fast this Boolean function. It's called cut, so we remove one object from the other, and simply like that, we have a hole in our object. So you can see everyone can do that. Okay? You don't need any expertise. And if you repeat it multiple times, you have this design here. And when you are done, you can select either export the design for another tool, or you go to the next step, which is the design testing. Here, you can have an interactive evaluation of your design without having to use a complex CAE tool. So that's, here in this case, that's a finite element example. So you can scale up and down. You can make it a little bit bigger, your model. Again, on the touchpad are all the information needed. Here, you just select where it's fixed. It's these small holes here. That's why I make it bigger, to make it easier, the selection of the holes. That's there, it will be fixed, because there we'll put the screws later. So we say that there it's fixed, it's really fast. and then we say where we want to apply the force. Again, with the controller, we change the menu. Now select where the force will be applied. And you select the surface there. And by selecting the force, now you are done. You go to the last option, apply the force. You just take your controller. By clicking the trigger button, you can define the magnitude and the vector of your force and get the result instantly. That's the deformation here. As you can see, as I move that around, it's changing the coloring. So everything is real time. And of course, you can read the values thanks to a virtual pointer that we have integrated, or switching to stresses to find the critical parts or the critical spots of your geometry, which, if you are satisfied with this first result, you can go further, or you can go back and improve your design. Now, because everything is coarse in the VR, it's not optimized, and it's really fast, we have integrated the next step to help you. That's a design optimization. We have integrated a topology optimization algorithm in the virtual world, which improves your model. So again, the same like before, you select which areas should be remain kept, like the blue ones. We don't want to change them because these holes will be used for the screws later, and we want to optimize the whole geometry. And then by clicking the optimize, we trigger the topology optimization, which runs externally from this VR world. It's a Siemens tool called Siemens NX. But the user gets a feedback on a monitor how the process is evolved over time. Here you can see how the geometry evolves during the topology optimization. In this case, it took us 15 seconds to have an optimized geometry. And when the geometry is optimized, then it's automatically stored in the system, and you can use it for the final step, which is the design evaluation. What's the design evaluation? Here it's evaluation in XR because it's a cross-platform. We can use this evaluation with all the types of VR, AR hardware we have tested so far with the Vario, HTC Vive, Oculus, Android, iOS devices. So here, the R&D member can investigate the results of the topology optimization. If you remember before, it was 2.2, the deformation. Now, after the topology optimization, it's only 0.6. So you can see that's improved. And he can leave some annotations there for some results. And if he's not sure about the results, he can call an expert and meet in this virtual world. With a tablet there, that's Dirk in the US, I'm in Munich, and we discuss about the results. And I leave some annotation there and ask him, what do you think about here? And it goes the other way around. He can go with the tablet around this geometry and place his tags, and then we can, in this way, discuss the results and have the improved design really fast. So we improve also the relationship between the team members and make effective the communication. But that's, you may say it's only great, it's a concept, how it's in real life. We have carried out some preliminary studies. We asked 19 persons to carry out a certain task, which to construct a geometry, a predefined geometry. And we asked them to do that with two different tools. One is with the open source free CAD tool. It's a tool that we can make a CAD tool which can construct geometries, and the other is you can use our concept, the CAD VR part. And you have only 20 minutes to realize that. And what we figured out is, that was also astonishing for us, 90% of the people managed to realize all the steps and complete the geometry with using our tool, where with the open source program, only 25% of them managed to realize that. And for the open source, we provide them some instruction where to find the basic functionalities. And what's even more astonishing is that with our tool, they managed to do twice faster the tasks that were fulfilled with, from all the people. And there is another factor called usability factor, SUS. You can find more information here on the internet about the evaluation, where it's 80 score out of 100, where the free CAD had only 50. And that's another, that's here, we tested that later this year, previous this year, on real cases. For example, here on the left side, you can see that's one hardware from our portfolio, that's from Healthineers of Siemens. You can see it's called C-arm, and we said, okay, we want to have a concept how we can improve this C-arm, how we can improve the design. And we went to 100 simulation experts and asked them, okay, what do you think? How much time do we need to improve the design? And the average answer was 2 days. And as you can see here, we went back to our concept. We did that live in a simulation conference internally at Siemens. We did that live so everyone can believe us. We start from this design, and we have this optimization part in just 30 minutes. So you can see a speed up of 2 days, I would say, of the whole process. And the previous result that you saw before, that's a design for a real experimental facility. That's a support construction for sensors, which we mounted on our electric motors. And a typical workflow for that would be half a day of our work. So to go to the design tool, evaluate everything. And with our simulation concept, it took only 5 minutes to realize that. So before closing, I have to give my credits to the whole team because it's not my personal work. It's more than a 2 years project, as I said, and multiple persons have worked with me, and the credits should go to them for their help. And if you want to learn more about our activities or these demos, you can contact either me or my colleague. Thank you very much for your attention.
Thank you, Theodoros.